Hey guys, your boy Chili here. Welcome back to Hardware 3D Tutorial 47 Part 1. In the last tutorial, we learned about full screen post-processing filters. We implemented a very basic blur filter. Now, this tutorial was quite a long boy. I did a little poll on YouTube, you might have noticed it, and I asked, would you like to have a long boy or would you like to have two shorter boys? And you guys, it was pretty good indication that you guys wanted shorter boys. So I'm going to split this tutorial up into two parts. The first part, this video, we're going to do a little fix up on the quality of our full screen filter. I'm going to fix a little artifact in there. Then we are going to apply our blur filter to the outline effect. We're going to create our blur outline effect, and that's going to fix the problems that I introduced at the beginning of the last video. And then finally, in this video, I'm going to hit you guys with some hardcore theory on a little bit more advanced filtering techniques. So like I said, the first thing we're going to do is fix a graphical artifact to give a nice quality boost to our box blur filter. So see if you can notice an artifact in our blurring effect here. So I'm moving the camera here. What do you notice? Well, look at where our light is, and then look at the bottom of the image here. And you can see that there is a little band of light here at the very edge of the image, and that corresponds to where the light is at the top of the image. And notice also in our image here a band of darkness at the very borders, and this actually goes back to the thing I mentioned. It's the question of what do you do at the very edge of the image here when you don't have a full set of input pixels to work with here. When you look at the very top corner here, you've only got 4 input pixels to work with. So what this example has done is it just doesn't render pixels at the border. But what's happening with our situation? Well, let's say we're executing our kernel here. So it's going to try to read neighboring pixels. It's going to try to read pixels that are below our off-screen surface. And with our current texturing system, we have set it to wrap texture coordinates. So when it goes beyond the edge of a texture, it's going to wrap around to the other side, and it's going to be reading the pixels, whatever pixels are there. And if they are much different than the pixels on this side, you're going to get a weird artifact. Take a look again as I move this. You can see this weird artifact on the bottom as the light moves around at the top there. So what we're going to do is we're going to modify our sampler bindable just a little bit. We're going to add 2 flags when you create it. One flag is whether or not you want to enable anisotropic filtering, and the other flag is whether you want to have textures that reflect. And what texture reflection is, well, let's say you're trying to read past the bottom of the texture. If you were to wrap, you would be reading here. But if you were to reflect, you would read here instead. So that will enable us to read a pixel that is pretty close to the place where we want to read from. Another option might be clamping, but I prefer reflection here, personally. So yeah, we have those options here, and then in the constructor, we check to see if we have reflect. If so, we set D3D11 texture address mirror. Otherwise, we set it to wrap. And we'll also be able to enable anisotropic filtering. If I disable anisotropic, then I just want the point mapping, just nearest point. Because for the full screen filter, the way we're using it right now, we're just sampling at the centers of all the pixels. So we don't need bilinear filtering, and we don't need anisotropic filtering. So I added the option to turn it off. And then in Frame Commander, we create a separate sampler for our full screen rendering, and we create it with anisotropic filtering off and mirroring on. And then we set that sampler when we do our full screen funky pass. And now you see if I move this view around so that the light comes in and out of view, doesn't affect the bottom of the screen whatsoever. Looks good. All the borders now look a lot nicer. They don't have that black ring. Alright, so that's a nice little trick for you when you're making screen space post-processing filters. Remember your oversampling mode. Reflection is good. Clamp can also work, but wrapping is going to give you problems. Alright, so let's look at the next commit here. Now the name of the commit doesn't really say much about what it is, but this is actually where I take the blur filter and I use it to implement that improved outline effect that I talked about in the previous video. So you might be wondering, well, Chili, how are you going to use blur to create an outline effect? Well, it's not that hard. So you draw your object normally, right? Like this. Now with our outline effect, our original scaling outline effect, you would then draw the geometry again with a solid color, but you would use a stencil to mask out the stuff from the original drawing, so you'd only get this outline. All right, and the blur outline is actually quite similar to this. So instead of drawing the object scaled up, you draw the object again with a solid filter. So it's going to look filled in like this. You don't do any stenciling or anything, you just draw it solid. Then you apply the blur. So applying the blur will give it like a blur halo. All right? And then you take this and you composite it onto the original object's image with stenciling. And the end result is, because you're stenciling out the solid part, all that remains is the halo. And so you get a nice glowing halo around your object for your outline. And this is done in screen space, so it doesn't matter how far away the object is. This distance here, the radius of the outline, should stay the same, and it shouldn't, be affected by all those nasty problems that I showed you at the beginning of the previous video. So let's take a look at the changes that go into implementing that. First one, the blur pixel shader doesn't change at all. I just change the radius here, but I leave everything else the same. So it's the blur that we had developed in the previous video. All right, now the big change here is going to be in the frame commander, because this is going to show all the steps of the rendering process. So you can see I renamed it from Func PS to Blur PS, but otherwise pretty much the same. Setting up full screen, we add a blender to our set of full screen binds because we want to be able to set the blending mode. So what are we going to do in our frame? Well, we're going to clear the depth stencil. We're going to clear the off-screen render target. We're going to bind the swap buffer. And we're going to do our normal drawing. So we're going to bind our blender here, and it is disabling alpha blending. We're disabling stenciling for all the draws, and then we're executing all of the jobs in our draw pass. Next, we create our outline mask in the stencil buffer. And you see this code hasn't changed. It's the same as before. We don't need a pixel shader. We just want to set the pixels or the values in the stencil buffer for masking later on. Now here in the outline drawing pass, we are going to bind our off-screen render target now. Stenciling is off, and we execute the jobs from the pass number 2. And then the final pass here brings it all together. So we're going to be binding the off-screen target now as a texture. It's going to be the input. The output is going to be, where is it here? Yeah, the output is the swap buffer. So right now, remember, the swap buffer contains our normally rendered scene using, our Phong rendering shaders. So we're going to be outputting to our normal scene, inputting from our blurred outlines. And you can see here, we're going to enable the stenciling so that when we draw from the blurred outlines onto our normal scene, only the halos are going to make it through. The actual objects themselves, they won't be overwritten. And an important detail here is we're going to bind our blender, our full screen blender, and our full screen blender has blending enabled true because we want to blend those halos on top of our normal scene. A couple small changes to render target, just add the ability to clear the render target with a specific color if you like. And then in material.cpp, for the outline technique here, we're changing from the offset vertex shader to just a solid vertex shader. Because remember, we're not offsetting the geometry this time. We're drawing the silhouette, same size and same vertex positions as the original geometry. So we don't need this constant buffer anymore for the offset vertex shader. We can remove that. But everything else stays the same here. And yeah, here you see the final effect, and it looks pretty good. We can rotate our cubes. The outline is looking pretty good, but all is not perfectly well in the world here, because if we get in close on this boy, we see that our outline, this width is actually getting larger depending on distance, and it shouldn't do that. It's in screen space. So there's something wrong with our system here. It's not perfect. It's looking pretty good, but not perfect yet. And we can see here the problem was that we still had the transform cbuff scaling in here. So it was still scaling up the geometry by a little bit when it shouldn't be. So we replace all this stuff here, this inline class, with a very simple, just standard transform cbuff. So here's what it looks like without that geometry scaling, and yeah, it's looking better now. If we zoom out like real far, the outlines, they don't get any thicker in screen space. We can get in there real close and still the same width for these outlines. By the way, in case you're wondering why we can composite this onto here and it blends nicely with the underlying image, when we clear the off-screen surface, we clear it to 0, 0, 0, 0. So the alpha is 0. And then when we draw this outline here, we draw it with an alpha of 1. And when we blend using our kernel, our blur kernel, in a position, it's going to average between these pixels, their alpha of 1, and these ones, their alpha of 0. And as you travel in this direction, the halo, the alpha is going to go from 1 on the very edge here to 0 on the very edge here. So the blur filter not only smears out the color, it also smears out the alpha, and that gradation of alpha blends nicely with the background. Now the problem with this is that we're not only blending, like if we take this cross section here and we look at it, we're blending the alpha like this, but we're also blending the color. So here we have low alpha, but the color is black. And here the color, there's quite a bit of black in the color here. And here the color is all red. So when you blend, let's say this point onto the scene, you're actually blending some black onto the scene, which can make it darker. We only want our halo to make it lighter. So what my idea is that I would like the color in this band here, as you travel outwards, the color should remain the same. It should be the same red, and only the alpha should go down. So when you blend it on top of the scene, you're not blending black on top of anywhere. You're only blending red, but the amount of red that you blend goes down as you go outwards. And that, my friends, is what this commit is all about. Improved blending dark band with max. So what we do here is when we apply our blur filter, we accumulate the alpha channel as usual, and that will be divided by the divisor. But for the color, we just take the max color from all the input samples. So in the 3 channels RGB, we take the max over all the pixels under the kernel, and that gives us our color that is used for the output pixel. So we're not averaging the color. If the color under one of the pixels under the kernel is red and the rest are black, it's just going to max out to red, which is what we want. We want a constant color that is smeared out, but that remains constant intensity. And we want an alpha that is smeared out, but that gradually rolls off to 0. And here's the effect of that. Notice I didn't change the radius of the filter at all. All I did was I changed the way we were dealing with the color and the alpha. But you can see here, it's a much bolder outline now. Before, we had a radius of 12, but there wasn't much outline to it. It was pretty weak. And that was because we were blending with black. But now we're not blending with black, we're just taking the maximum. And we're only blending out the alpha. So we can see here, this is already pretty darn good. And interesting thing here now, it takes the maximum. So when you've got these 2 outlines that overlap here, it's going to take the maximum of the 3 channels and kind of combine the 3 channels together. So you can see here, if I do green and red, it combines them to get yellow at the intersection here. A little interesting effect. All right, so we did a little bit of blurring. We got a basic blur outline effect working. Now let's take a look at some more advanced techniques and theory. So let me posit to you guys something. We've got our filter here, our kernel, and we've got an input image that has a single pixel lit. So I mean, if we execute our kernel and it's working at this position here, it's going to output, you know, all these pixels divided by some value. It's going to be, you know, a light gray color in our output. Now, if we're to execute the kernel here, what's the output? Well, it's the same. It's the exact same shade of gray, right? Because you've got all black except for this one. You add them all up, you divide by whatever maybe 25 or something. I don't know. It doesn't matter. But the thing is, in blurring, if the thing is pixels closer, shouldn't it have a greater effect than thing that is far away? I think it should, right? But with our current filter, which is known as a box filter or a mean filter, it just performs an average. It doesn't matter how far that pixel's away. They're all equally weighted. You just add them up and then you divide by some value. But you can get a better effect if you weight them so that inputs that are very close contribute more to the output than inputs that are far away. Now the kernel for that is what would be known as a Gauss curve or Gauss function or a normal function. And it looks like this. This is also known as a bell curve. And you can see here, things farther away are weighted much smaller than things that are very close. You can adjust, the proportions and everything, the shape of the curve, but it gives you a better result. Here's the idea of, in 2 dimensions for an image convolution, what a Gauss looks like compared to what a box filter or a mean filter looks like. And the results for the Gaussian are better. I mean, you get the blurring, but you lose less information. It's a much more natural effect. You can see here, box versus Gauss, box filter versus Gauss filter. So the question is, how do we implement this? Well, instead of just using, equal weights for all the inputs in our kernel, we are going to apply different weights. So we're going to store a kernel like this. And, when we read this pixel, we're going to multiply it by this weight. We read this pixel, we're going to multiply it by this weight, etc., etc. Now, to figure out these weights, you need a function. So this is the function that you generally use. It's called a normal distribution. It looks kind of scary. It looks kind of freaky. But what it really is it is just exponential of x squared, where x is the distance from the center of the kernel. It's got a couple of parameters. This is the mean, so this indicates the center of the bell curve. And then this parameter here is the variance, and it basically controls the fatness of the curve, how steeply or how quickly it falls off. And you just plug the values in, you can calculate it for all the different pixels in the kernel. Now, to be perfectly accurate, you wouldn't use it directly like this because you have to integrate it and sort of adjust it so that the sum of all the weights is 1. We're not going to worry about being super perfect about this. So basically, we're loosely going to use this formula to generate a kernel of values that is going to be something like this. And if you were to plot that kernel as a graph, it would look something like this. But there's one more thing that we're going to add. There's one more little spicy meatball we're going to add here. So you guys should be familiar with the idea of a kernel by now. You're going to scan that kernel over the entire image. And, for every position, you're going to sum up all the pixels under the kernel, multiply them by, some weight of the kernel, add that all together, and that's your output. And you're going to do that for every pixel in here. Now, we can actually do this in a little different way that gives us a nice performance benefit. So let's say our filter here is a box filter. This boy here. We can actually represent it. We can split it up or separate it into 2 parts. A horizontal part and a vertical part. So if we do it this way, we have to take 2 passes. So in the first pass, we're going to apply this horizontal convolution filter to the whole image. And what is the output of that going to be? Well, what this one is going to do is it's actually going to blur it, but it's only going to blur it horizontally. I mean, look at the shape of the kernel and it's pretty clear. If it's right over top, it's going to be black. But down here, it's going to be gray. And here, it's going to be gray. And if we move it here, it's still going to be gray. So running this over the entire image is going to smear it out in the horizontal direction. And then on this image, we run the vertical. It's going to smear it out in this vertical direction. And in the end, you're going to get a blurred square, which is exactly what you would have gotten if you had applied this square filter one time. So by first applying this horizontal blur plus this vertical blur, you end up with the same result as applying this one. But here's the catch. let's say this filter, let's say your image here, you know, for argument's sake, 100 by 100 pixels, which is, you know, 10K pixels. Your kernel, 5 by 5. So that's 25 pixels. So the amount of pixels that you need to sample to generate the output is the number of input pixels, 10,000, times the number of samples per pixel, which is 25. So you're looking at 250K for this one. Now, if you were to do it separated, first horizontal, then vertical, well, what do you got? You've got 10K times 5 plus 10K times 5. That's 100K. So by doing it separated, you only have to sample 100K pixels. If you do it combined, you have to sample 250K pixels. That's 2.5 times more work to do it this way than to do it separated. So if you can separate out your kernel into a horizontal and a vertical pass, then it's going to be a lot less work. It's going to be more optimized than having to do it all in one go. And you can also do that for the Gaussian. So the separated horizontal and vertical for a Gaussian is just a one-dimensional Gaussian curve. So you got one-dimensional Gaussian curve in this direction, one-dimensional in this direction. If you apply that horizontal and vertical, you get the same result as, you know, your two-dimensional Gaussian thing that looks like, I don't know, like this. I can't draw it. A three-dimensional thing. Doesn't matter. The moral of the story is you can separate a box filter into horizontal and vertical, and you can also separate a Gaussian into horizontal and vertical. You can't separate any convolutional filter that way, but many of them you can, and it makes your work faster. And then we don't have to generate an entire kernel, X and Y, 25, you know, values for a kernel. We just have to have a single one-dimensional kernel set of values here, and then we can use it for the horizontal and the vertical passes. And that's what we do in the code, which we can finally get to now that I've gotten through this theory. But that's gonna have to wait for another day. Yes, we're cutting it right here. I'm gonna give you the blue balls. They don't call me the king of cliffs for nothing. So stay tuned for the next video. Got some good things lined up. Obviously, we are going to implement all this theory that I just described here. We're going to create a Gaussian blur filter. Then we're going to apply that to our blur outline effect. We are going to then make the blur outline all dynamic. You'll be able to change the blur radius and the shape of the normal distribution, the sigma, all at runtime with sliders. After that, we're going to look at a little optimization technique for the blur filter that'll give you an effective 16-fold increase in performance. That's huge. And finally, for a little treat, I am going to then take you guys on a little tour of the post-processing effect via the graphics debugger. We're going to look under the hood. We're going to see all the intermediate steps. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. Helps a lot. And I will see you soon with some more Hardware 3D.